You know, okay, this one is what? Okay, found it.
I just started once.
One minute left. Do you know?
I tried it.
So you won't need this. You won't write on this, right?
You're writing on the whiteboard.
Let me see if that actually looks nice.
Yeah, I did my presentation here. Very nice. It depends on each person.
What's it you train? Oh shit.
What is glass time thing? This is LLM. Yeah, this is my stuff.
Delete it.
No, I can't, bro. My heart hurts.
Because I'm doing it.
We're gonna use the whiteboard. It's fine.
What's his life support? He's taking away. What? He's taking away a life support.
Yeah, you can do this. No, this.
Yeah, no, bro, I'm not using this shit.
Why?
I think it's too. It's too.
You can make it
Not easy to
and I have to leave those there for the... I mean, it's big. This is also going to be like... No, es parte para este topic. Should we start? Bueno, como siempre. Yeah, it's really fun. Voy a recibir introduce them, okay? It's the subject, I introduce them. Introduce the subject, I say about the book. Yeah. Where mass is cinema. It's not very common, but it's
It's a good time.
Just put it. Is there a specific reason? It's not problem. So, hello everyone. So, hope you're all doing well. I am Ahmed, and co-president of the Math Society with Loredana. And today we have the second episode of our series of the topic tutorials that we're preparing with the Math Society, which is namely called When Math Meets Cinema.
Today we're going to present the math behind some key topics in Interstellar, and our presenter will be the freshman Pratixit and the second year Thushar. Hope you enjoy.
Please, a round of applause for them.
So today we're going to talk about Interstellar, a tale that follows Cooper, whose entire story is that he's a NASA engineer, also a pilot with an engineering background. Pardon? Someone say something? Never mind. An engineering background that, let me rewind again. NASA engineer with an engineering background. It's a larger-than-life tale which follows the story of this guy who's trying to save humanity in its entirety. Humanity is dying, there's no resources, and you need to leave the planet.
And of course, it goes without saying, but major spoilers ahead. So if you don't mind that, I mean, then it's all good. Now, we talk about what is Interstellar. What do you have to say?
Interstellar is a big-ass movie released by Christopher Nolan in the year of 2014. It's a science fiction movie. Our job today is to see how much of it is science fiction and how much of it is actual reality. And that's where the math comes behind it. There's adventures, drama, it's a lot of... go slightly back up. It's a lot of adventure, a lot of drama, a lot of tears being brought down from our own eyes and the characters' eyes themselves. The main cast is, of course, Matthew McConaughey, an amazing actor who plays Cooper himself, Anne Hathaway, who's the daughter of, again, Cooper, who's played by Matthew McConaughey, and Michael Caine, the old dude who's in all of Christopher Nolan's movies, also a cool guy. And again, beautiful, beautiful track composed by Hans Zimmer himself. If you don't know, if you've not watched the movie, you must have heard this track somewhere or the other. This track is beautiful. It brings together the movie in its entirety. Without this track, the movie is nothing. Without the movie, the track is nothing. It goes hand in hand. And again, a lot of inspiration from Kip Thorne, the Nobel Prize-winning physicist who sort of actually derived formulas to help bring a lot of the visuals, like, such as Gargantua, like big ass black hole that you see in this movie, and a lot of the scientific visuals that you see, the VFX, all is sort of grounded in reality. But again, not all of it is, and that's where he comes in to present the math. Let's go to the next slide.
I mean, we've already gone over the synopsis. We know what the movie is about. That's a prerequisite to this presentation. But even if you don't know, Thushar's done a wonderful job.
Again,
Okay. Now, the main question I want to answer today, two main questions, are one, is Miller's planet really as far away from Gargantua as the physicists claim it to be? And is the solution valid? And the second thing delves into the shape of the universe. I'll explain how both work into creating the world of Interstellar, but to find out how far away Gargantua is from Miller's planet, we must first have a look at the tidal waves, and it'll make sense in a second.
And when the ad is playing some context, Gargantua is
Darum lohnt es sich, ausgezeichnetes Obst und Gemüse zu säen.
mentioned is where all these characters go to, and there's time dilation happening, and so time moves faster.
Weil wir damit mehr ernten als Lebensmittel. Wir ernten beste Qualität und euer Lob. Das lohnt sich. Danke, dass ihr uns zum 9. Mal zur Nummer 1 für Obst und Gemüse gemacht habt.
Please don't buy anything from here. Work.
Mit Birnen 1,5 Kilogramm in der XXL-Packung für nur 1,79. Lidl lohnt sich.
Very graceful.
No, but very efficient. What are you waiting for? Let's go. Go, 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 go. 7 years per hour here. Let's make it count.
This way. About 200 meters.
Gravity's punishing.
Been floating through space too long?
130% Earth gravity.
There's nothing here.
Should be right here.
If there's signals coming from here. For beacon.
Wreckage.
Where's the rest?
Towards the mountains!
Those aren't mountains. They're waves.
Oh shit. Oh shit.
That one's moving away from us.
We need the recorder.
Doyle, back to the Ranger now.
We're not leaving without her data.
Get back here now. We do not have time. The second wave is coming. We're in the middle of a swell.
I got it.
Get your ass back to the Ranger now. Rand, get back here now.
Go, 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 go. I can't make it. Go.
Pace, go get her.
was saying, the beautiful score that you hear, each ticking sound that plays exactly at 1.25 second intervals represents one day passing on Earth. And small details like this that you would not notice on the first watch is something that you realize on your third, fourth, fifth, sixth rewatches, and YouTube videos that you watch again and again to get smaller details that you just don't notice. And this is why I love this movie this much, because of the nuances that are there. And it's just a lovely scene.
Alright. Now, you might be wondering how these tidal waves will end up telling us how far our endurance is from Gargantua, but I'll tell you how. But first, a little bit of trivia. Since the movie released, as per my calculations, and I'm no expert, but 1 hour and 34 minutes have passed on Miller's planet. Moreover, the waves in this scene are described as being 1.2 kilometers high, as per the Science of Interstellar by Kip Thorne. The physicist who worked on this wrote a book, and that is where I'm getting the data from. But what I really want to know as a mathematician is this consistent? Is this valid? Now, as we do that, we need to delve into a little bit of physics and look at the tidal acceleration. Now, I won't go into the derivation of how you get this expression, but you can get it by computing the vector sum of the gravitational force through which Gargantua is pulling Miller's planet and the centrifugal force that Miller's planet experiences as it orbits. Now, the A vector is similar, because this is still an approximation, this is not an exact figure, but it is similar to Newton's constant, which is 6.674 times 10 power negative 11, multiplied by the mass of Gargantua, which is the big M, y, which is the vertical position of the tides, divided by d cubed, which is the distance from Gargantua to Miller's planet. And all of this is then turned into vector form by considering a unit vector, E sub y. Now, I'd like to pull your attention to a little bit of the mathematics here. We know that the acceleration that is experienced by the waves on Miller's planet is given by this expression. But how do we connect it to the distance between Gargantua and the Miller's planet? Well, it's quite simple. We take something we know. That is exactly how we work in mathematics. We take something we know, we take something we have, and we try to connect them and find the unknown. That is exactly the mathematical method at play here. We know that the work done per unit mass on every particle in the waves on Miller's planet can be given by r, which is the distance from Miller's planet's surface to the wave's height, multiplied by the average acceleration. To find the average acceleration, we use something called as the mean value theorem for integrals. It works very simply. You see, you think of an integral as summing up from one bound to another. That's all. That's the intuition behind it. And you divide it by the bound. So you're used to 1 plus 2 plus 3 plus 4 plus 5, all divided by 5. Well, I present to you the continuous form of that, where you sum from 0 to r, and then you divide that by r to get the average acceleration. When you do the math, you see that we integrate with respect to y, which is the height above the surface of which the tides live at. And then you do simple integration and you get the following expression, that the average acceleration experienced by the tides particles is given by 3gmr over 2d cubed, where d is the distance from Gargantua to Miller's planet. Keep this in mind because it's truly amazing. Now, by the work energy theorem, whatever work that a particle must do or a body must do must be equal to the potential energy that is stored. And in this case, the only energy that the tide has is gravitational potential energy. So yet again, we consider the gravitational potential energy per unit mass, but even if you don't consider that, the masses cancel out because we're considering the masses of particles, which remain consistent. Now, we say that the gravitational potential energy per unit mass is equal to the work done per unit mass. This is how it all comes together, because now we know that G is equal to Gm over R squared. How do we know this? It's because of Newton. He showed that for a planetary body, at the surface of any planetary body, the acceleration due to gravity that it experiences is given by this expression. And we know that the work done per unit mass is given by this. Boom, bingo. We have an unknown, and we have something we know, and we can find the distance between them. So we do some simple algebra here. We cancel out the G's, we cancel out the M's, we take R that side, we take D that side, all that jazz, and we end up with this expression. D is equal to the cube root of 3m power 4 all divided by 2mh. Now I'll explain what these terms mean here. R is the radius of Miller's planet. H is the height of the tide of the wave of the tide. M is the mass of the planet, and the big M is the mass of Gargantua. When indeed you perform these calculations, you will see that it concludes to 4.5 billion kilometers away from Gargantua's center. Now, my question here is this solution valid? And it actually turns out that it's not. Reason being, can you have the next slide?
Can you hear what?
You need the next slide. Reason being, when you consider the time dilation, it is, in fact, inconsistent. Now I'll show you how. We know from the movie that each hour on Miller's planet is equal to 7 years on Earth. Now if you use a bit of basic ratio and proportion, we get that the time dilation factor must be equal to 6,000. However, there is an existing formula for the time dilation factor of a planet or any celestial body orbiting a black hole, and that is given by this. Now I'll explain the terms here. G remains Newton's constant, which is 6.674 times 10 power negative 11. C here is the speed of light. M is the mass of Gargantua or the black hole, and D is the orbital radius. Now for simplification here, we consider that the orbital radius remains constant and is not elliptical, but it is rather circular, so that we can get an answer. And the answer you get is surprisingly 1.05, not even close to 6,000. So now, this is where the fiction part of the science fiction really comes into play. Because when you think about it, these things don't exist. I mean, Kip Thorne did his best to try and be consistent, but at the end of the day, this is science fiction, so there are bound to be inconsistencies. But that is not something that we need to be deterred by. Rather, we should appreciate the fact that so much work was put into the movie, and that should motivate us to make our theories even more accurate. Now, another question that I had when I first watched the movie is, how did Cooper not get spaghettified when he fell into the black hole? Major spoilers, I know, but I hope you were prepared for that. Well, I'll show you with this scene what happens, and I'll show you why I think he wasn't spaghettified, or at the very least, the explanation for why he wasn't spaghettified, as per the movie.
Brauns bester Rasierer für perfekte Gründlichkeit und höchsten Hautkomfort. Braun, Qualität made in Germany.
Spürst du die Zeichen der Zeit? Zentrum Vital Plus unterstützt Knochen, Knorpel und Muskeln.
All of this is one little girl's bedroom. Every moment. It's infinitely complex. They have access to infinite time and space, but they're not bound by anything. They can't find a specific place in time. They can't communicate. That's why I'm here. I'm gonna find a way to tell Murph, just like I found this moment.
How, Cooper?
Love, Tars, love. It's just like Grant said. My connection with Murph, it is quantifiable. It's the key.
What are we here to do?
Find out, tell her. The watch. The watch. That's it. We code the data into the movement of the second hand. Tars, translate the data into Morse and read it to me.
Translating data to Morse. Cooper, what if she never came back for it?
She will. She will.
Murph, I can see his car! He's coming, Murph! Okay, I'm coming down.
How do you know?
Because I gave it to her.
Roger Morse, dot, dash, dot.
Dot, dash, dot.
Dot, dash, dot, dot.
How do you know?
Because the bulk beams are closing the Tesseract.
Don't you get it yet, Tars? They're not beings. They're us. What I've been doing for Murph, they're doing for me. For all of us.
Cooper, people couldn't build this.
No, not yet. One day. Not you and me, but a people. A civilization that's evolved past the 4 dimensions we know. What happens now?
Alright. Now, a very heavily discussed topic about this film is about how Cooper got back home. Black holes, wormholes, white holes. I don't want to delve into any of that. Rather, I want to delve into what this scene reveals about the shape of our universe and the topology of it and what it actually means. Brain cosmology. What this theory basically talks about is our universe is divided into 3 brains, and brain here is short for membrane. What it proposes is that our universe is in the middle of 2 sandwiching brains, and these 2 sandwiching brains allow for the interaction between our universe and higher dimensions. And that is precisely why what happens when Cooper falls into a black hole is that he's transferred from this brain that we live in to a confining brain. And what that confining brain allows him to do is be in a tesseract that is 5th dimensional. Now, of course, we've all heard about general relativity, time is the 4th dimension. No, that's not what I'm talking about. I'm talking about an n-dimensional space in which a 3D being was embedded. What that does and what that means is now exemplified by the mathematics here, which talks about Einstein's field equations and in particular tensor calculus. I will spare you the grudging details and everything that you have to go through to get a system of differential equations so that you can get an answer to what the shape of the universe really means. Let me explain the equation first to you. On the left hand side we have what's called the Ricci curvature tensor. Intuitively what it means is that this tensor, this mathematical object, it describes how at a particular local point space is curved. On the right hand side, we have what's called the metric tensor, which tells you the geometry of that local behavior. And these 2 tensors are connected with what's called the cosmological constant. This cosmological constant is extremely, extremely important to finding out the shape of these brains and in particular, the solution of them. What I want to propose here, what I want to tell you about, is that these Einstein field equations can be reduced to a set of differential equations, with this one in particular being the one that's solvable. Now, I'll show you the other equation as well, and you can verify for yourself if this differential equation, the solution to this differential equation indeed satisfies the other one. But for simplicity's case, just trust me on this and know that that tensor calculus system boils down to this simple first order linear differential equation system. We have 1 minus 2r times f prime times f minus f squared is equal to the cosmological constant multiplied by r squared. Now here, f is really f of r. What this means is, what we're looking for is a solution to this metric. The coefficients are missing, I'm sorry for that. But over here we have an f squared r, and over here we have an f of r. what we're really looking for when we say we're looking for a solution to the metric that describes the shape of the universe is solving this f. This f is constrained by this particular boundary condition, which is the cosmological constant, multiplied by r squared. So it's a very simple differential equation calculation. You have to observe that if you let y equal f squared, we'll get y prime is equal to 2f prime. 2f times f prime. So what this differential equation ends up becoming is 1 minus 2y prime minus y is equal to this cosmological constant multiplied by r squared. I understand this is a lot of mathematical jargon, but at the end of the day, I am talking about the mathematics behind Interstellar. Now, when you try to isolate and solve for y, what we notice is that once you put one to the other side, you get ry prime plus y is equal to 1 minus cosmological constant r squared. Notice that ry prime plus y is simply the differential of the product r times y. You can think of the prime as differentiating with respect to r, and we differentiate, yes?
I just have a quick question.
Yeah.
Does f describe the shape of the universe?
No, f does not describe the shape of the universe. It is simply a non-linear coefficient that we're looking for that satisfies the following metric.
So why do we need to find f?
We need to find f so that when we find f, this metric is solved. And once this metric is solved, you can then describe the shape of these branes using what's called de Sitter and anti-de Sitter spaces. So that's basically the goal of it. The goal of this exercise is to find this f so that then this metric defines the shape of the universe. Now, what happens here is you can then do some simple integration with respect to r and find that ry is equal to r minus 1 over 3 cosmological constant r squared, and then there should be a plus c over there. Plus c. Now, when you just divide everything else by r, you get that y is equal to 1 minus the 1/3 of cosmological constant r squared plus c over r. Now, you might be wondering, what do we do with this c? Because we don't exactly have a boundary condition to solve for the differential equation. What we do then is we look at the physical meaning of this constant. Now, when you notice that when you take this y as the closer it gets to 0, if c is not equal to 0, then that term blows up to infinity. It becomes infinitely large. And when you look at space-time singularities in our universe, it doesn't make sense. It's not allowed. You can't have terms that blow up to infinity. Right. So we demand by the condition, by physical intuition, that c must be equal to 0. Now, we get the following equation. F is equal to 1 over 1 minus 3 cosmological constant r squared. This still looks a little bit ugly. So we simplify it by letting this cosmological constant be another variable, and we get the following solution. So we found f of r, we've solved our metric, we can describe the shape of the universe, but all this while I've been excluding a very important thing about all of these equations, is that I haven't taken into account the sign of the cosmological constant. This is where the solution comes in, and this is where I will talk about the anti-de Sitter and the de Sitter spaces. Now, the initial equation that I put on the board, the tensor calculus equation, you have to, yes, these are the constraints. If you don't want to believe me, you can put in that function into this equation and you will yield the following result on the RHS. On the right-hand side, I'm sorry. Now, what I want to talk about, sorry, can you go back? Okay, you know what, it's fine. Alright, so when you solve for f of r, what you're really thinking about is, what does the shape of the universe look like? And what ways is the metric affected? That is where the sign of the cosmological constant comes into play. Here, all this while we've assumed that the cosmological constant is in fact positive. But what if that was not the case? And this is in fact the case for what happens to Cooper. Can you help me? This is in fact what happens to Cooper when he falls through the black hole. He falls between the brains of the universe, and he is warped into what's called an anti-de Sitter space. The entire solution that I showed you up until this point is for what's called a de Sitter space. A de Sitter space describes a solution to the Einstein field equations for a positive cosmological constant. But in fact, for a warped space, for a distance to be crushed, you need negative curvature. And that basically means, if I use one of my cards for visual intuition here, if you think of positive curvature in this way, distances are getting enlarged. If you think about it this way, now there's an easy gateway from to get from one place to another. Distances are crumbled. Now, when you take that into consideration and change the sign of the cosmological constant to be negative, we have to make a little tweak. And the tweak is we have to make r squared equal -3 on the cosmological constant, or lambda, just so I don't keep on repeating myself. Now, what this really means is you're trying to find, let's say, if it makes intuitive sense. If this shape is described by a positive cosmological constant, then by intuition we can say that this shape should be explained by a negative cosmological constant. And the reason for the tweak of introducing a -3 is because this number is already negative. You can't square a number and then get a negative answer. No, that's not possible. We're not working with complex numbers here, at least not here. Quantum physicists, they may disagree, but over here, we're not. So, when we plug this one with the value -3 on r, we get that f of r becomes 1 plus r squared over r. So, the ADS, or the anti-de Sitter space, has the following function of r, 1 plus r squared over r squared. Now, the reason I went to first to de Sitter space and then to anti-de Sitter space is for two key reasons. One, solving the Einstein equations is already a very big task, and it's honestly a pain sometimes, right? So it's easier often in mathematics to work with a problem that is similar to another, and then tweak it to fit the problem that you have. That is exactly the method that I've implemented here. By solving the de Sitter space and using physical intuition, I found out the solution for the anti-de Sitter space. Next slide, please. Now, this anti-de Sitter space is a hyperboloid geometry, which basically means it's weirdly shaped. For our purposes, it's weirdly shaped, and it has a saddle-like shape which contracts distances. What does that mean for Cooper? Now you see, on our brain of the universe, Gargantua to Earth is 10 billion light years, but because these brains work in crumpled distances, they work in different geometries, in different topologies, distances are not the same. Also, by topology, I mean it's another property of the space of the universe, but it doesn't have to do with much with what I'm talking about here. The reason I mentioned topology is just for mathematical completeness and to make more sense of what I'm talking about. Now, because these distances are so crumbled, you see 10 billion light years is crumbled into one astronomical unit, which is 150 million kilometers. So Cooper is able to send these gravitational waves from the Tesseract, or where he was in Gargantua, all the way to Earth in a matter of practically instantaneously, right? And that's because of this greatly crumpled distance. However, science fiction comes back into play, because when you think about it practically, if light takes 8.3 minutes to travel 1 AU, how can Cooper send those messages back to Murph immediately? And not just across time. He's not just sending them across time. He's sending them across different brains in our universe, right? Another problem that the brain cosmology model has is that, let's consider these three cards. This is our card. This is the confining brain on top. This is the confining brain on bottom. Now, if you see, if I keep on pressing this, and I keep on pressing this, well, I'm not very good with cards, I'm sorry, but the model I'm trying to say is that if these confining brains keep on pushing on our universe, at one point, these cards will buckle. And once these cards buckle, the universe doesn't exist anymore, right? I mean, there's just too much pressure for the membranes to handle, and then the universe collapses. That's another problem with this cosmological model. Moreover, even if you want to consider quantum entanglement, there is a theorem in quantum physics called the no-go theorem, or the no communication theorem, which basically states that if there are two observers that are quantumly entangled, then they cannot exchange information instantaneously. What that means is, even if you consider these gravitational waves to be quantum in nature, meaning they don't follow the laws of classical physics, but rather delve into quantum physics, even then quantum physics does not allow it. Moreover, as I iterated when the first time I saw this movie, why wasn't Cooper spaghettified? It makes no sense given our current knowledge of black holes. But such is the nature of science fiction and such is the nature of movies, and so the complaints will go on. Now, all I have to say is thank you for listening to me. I am by no means an expert in this field. I am still a freshman, but I thank you all for listening to me and thank you all for all the opportunities. And moreover, I would urge you to join the Mathematics Society so that you can combine what you love and combine what you love with mathematics and explore and gain a deeper understanding of everything that we do here. Because truly, well and truly, everything in the world is inherently connected to mathematics. So everyone here, I urge you all to join the Mathematics Society, and I thank you all for listening to me and giving me this opportunity. And thank you to Thushar, and thank you to Ahmed, thank you to Loredana, and thank you to all of you. Any questions, by the way? I'm totally open, yes.
So the point of this whole talk was basically to trash the movie.
Yes, I mean, essentially yes, but more than that, I'd also say this gives us great motivation to appreciate the work that was put in to try and make sense of the movie. Because these are truly unexplored realms, you know? How physics works in n-dimensional spaces and what it all means. So I think more than trashing on the movie, I feel I personally was exploring the frontiers of physics in this space. Yes.
You mentioned that when Cooper wanted to send a message, it won't be instantaneous. You mentioned that, for example, the sun rays won't hit. But the sun rays are in space and it's linear. So how do you relate these?
I'm sorry, I didn't understand your question.
You mentioned because of the rays being crippled together, yes, that it won't be instantaneous and it's impossible. But then you mentioned an example of the sun rays coming down to Earth. How do you relate this?
Okay, so my point there was that the distance between Gargantua and Earth is already very big, yeah? But in real physics, when you look at our solar system, the distance between our sun and the Earth is on average about 150 million kilometers, or 1 astronomical unit. The point I'm trying to make here is, even if the anti-de Sitter geometry warped space so much that 10 billion light years is transformed into 150 million kilometers, there is no way that even if the gravitational waves were traveling at the speed of light, would they be able to reach Earth instantaneously as they do in the movie. So I'm not saying that the sun was crumpled or anything like that. I'm simply trying to make a point of how absurd it is that those messages could go back to her, not just through time, through different brains in the universe, instantaneously.
So one point that I'd like to make about your question, we are not shitting this movie. I love this movie. The reason I'm here is because I love this movie. And again, there's a lot of, if you've seen these reels on Instagram, they keep saying, oh, they won a lot of awards for how scientifically accurate that description of the black hole was visually, and we never images that look as accurate as that. And recently there was a picture of the black hole that came out, and it looked almost exactly similar to what these guys had. So talking scientifically, they had a lot of breakthroughs, and a lot of papers written because of this movie. And again, nothing is perfect, and there are caveats, and that's what we're exploring. There are a lot of caveats, but a lot of great things that came out of the movie. I'm sure you're talking about it. Yeah, you better be.
Any other questions, please?
Where can we find out more about this?
Okay, so 2 resources I'd really recommend you to look at. One is the book called The Science of Interstellar by Kip Thorne himself. Wait, what do you want to get to know more of? The math behind the movie or the mathematical concepts?
Yeah, so I would like to see if I can, for example, read more about these different spaces. I think I would like to know how this describes the shape of the universe in the way you describe it more precisely.
Okay, so for a good starting point from Interstellar, it would be The Science of Interstellar by Kip Thorne. That's a good starting point. And a book on general relativity, because I'm not an expert on the subject, I can't recommend a certain book. But I'm sure there are books on general relativity that cover anti-de Sitter spaces and de Sitter spaces. So those two are the ones I could recommend you.
I have one more question.
Of course.
Sorry. So do you think we will ever reach a model that accurately describes most of the physics that's going on?
I'm just a freshie, bro. I'm not even a physics major. I'm a math major. So, but I mean, given the indomitable human spirit, I'm sure at one point we will.
Thank you.
Thank you. Any other questions?
Okay, so before ending this talk, I'd like to mention one last point, please. So we can just.
I have a question.
Yes.
What made you choose this topic?
Well, I've always really liked Interstellar, and I thought this was a good way to just push myself and learn a lot. Because I mean, in the past week that I prepared for this, I've learned tensor calculus, half of general relativity, and I'm sure I'll forget this very soon. But the experience is what matters, I believe.
So thank you, Pratixit. So one last point I want to mention is that next Monday we have our first prof talk given by Professor Kevin. I don't know if some of you here already know Professor Kevin, but I mean, at least for the second year and third years I know him. They will tell you that he's definitely one of the best professors that we have in this university. So next Monday he's giving us a talk about the math behind game theory and how game theory works, and specifically how bluffing works in poker, and why bluffing works in poker. So what? Yeah, and why is it important? So it's happening next Monday. So I hope to see you there again. Yeah, it's gonna be a very interesting event. And thank you, Pratixit, again.
Thanks to Thushar.